Today, let's do some calculus in Mathematica. Let's first consider the example from last time. F of x equals x squared. Here's the syntax for how to enter the function. F is the function name. Use square brackets for inputs. When you first define the function, put the variable name and then an underscore. That's essential. Then equals, a single equal sign in the function formula. I often also put a colon equals there, but you don't have to put a colon. You do shift return to enter it. Once it's entered, you can type f of x without an underscore to see, hey, yes, f of x is x squared. And by the way, you can re-enter things. You can change things. If I change this x squared to an x cubed and re-enter it, hey, now f of x is x cubed. It's updated its memory to what is stored in the function f. I have not typed g of x, so I think g of x is nothing unless I typed it in a different session. Yeah, g of x is just g of x. I could clear f like this, clear f. And now f of x is nothing. But then if I re-enter f of x equals x squared, now f of x is x squared. You know, we did that kind of fast. You can define functions, you can clear them from the memory, is what we're talking about there. Mathematica certainly can do calculus. Mathematica, what is the derivative of f? What is f prime of x? 2x. Hey, that's the power rule. So that's one way to get a derivative. Once you define the function, you can type the function name prime of x. You can plug in numbers into these things. What's f prime of 5? It's 2 times 5 is 10. Yes, 10. You can plot both functions in the same picture. This is what I'll have you do for your assignment. So I type plot here with the capital P just like before. Square brackets. Now something different. Put curly braces. I'm going to not just type f of x here, I'm going to put a comma and also type f prime of x. Tab over and tell you to the right of this curly brace right here and put a comma and then give an x range, like I showed you last time, like -5 to 5 or something. If I enter this as is, I will see both the graph of f and f prime. There they are. So the blue graph is x squared. This orangish graph is its derivative, 2x. Mathematica picked the scales on the vertical axis to be -12 or so to +27 or so. But once again, if I put another comma right over here and type plot range with a capital P and a capital R, arrow made by a minus sign and a greater than sign, and then in curly braces, put a y min and a y max, I can change the plot range. I can, for example, go -5 to 5. There's a more typical kind of window that you would make on your calculator. Blue graph being x squared, the orange graph being 2x. Mathematica can certainly handle more complicated functions. Let me redefine f of x to be something complicated. Oh, how about e to the -x times cosine of 2x? Notice the capital E, like I mentioned last time, represents the number e. Capital C is necessary to use for cosine. Capital S is necessary to use for sine. Mathematica commands always begin with capital letters, and that includes ordinary kinds of functions involving things we're used to, like e and cosine. Square brackets are function inputs. Notice this is not square brackets here. You still do use parentheses when you're multiplying. You also can use parentheses for powers. I'm raising e to this entire -x power. Enter it. F of x has been updated now. Mathematica is spitting back the e in kind of a fancy way. That's okay. To save time, I can go back up to this line. I can copy and then go down here till I see a horizontal line and paste and re-enter this code down here. And I'm going to get an updated graph because it's a different function. Maybe I should pick a different plot range. -50 to 50, maybe. Which graph is which? Which is the f of x and which is the f prime? Well, if it's consistent with the last one, evidently the blue should be f and the orange should be f prime. Is that the case? Well, what if you didn't know it ahead of time? You can do another option in here to color these the colors you want them to be. If I put another comma and type plot style with a capital P and a capital S, arrow, and then in curly braces, say put blue comma red. Since f is first here, it will be blue. And since f prime is second, it will be red. Re-enter it. There we go. The blue graph is f of x. The red graph is its derivative. Let me change this function a little bit. Let me go back up here and make the exponential decay not quite as fast by putting a -0.1 in front of the x. That'll still be exponential decay in an oscillation, but it'll be a slower exponential decay. Re-enter it. It has been updated. I get a graph that's different. Where's the exponential decay? It doesn't look like it's there. It is. Maybe I should change it again. Let's try -0.025 here. It's there. You just can't see it as clearly. This would be an example of a function that could represent a mass on a spring moving back and forth. And because of the exponential decay, e to the -0.25x, it actually involves friction. This could be a mass on a spring, a block of wood attached to a wall, say, moving back and forth, left and right, say, we're ignoring gravity, because you pulled it to the right, say, and let it go, and the spring is causing it to move back and forth because of the forces it exerts. And even if it was on top of ice, in a vacuum, there would still be internal friction from the spring that would cause the amplitude of the oscillation to get smaller and smaller. And that's what we're seeing with the blue graph. Let's change this to being, say, 0 to 10 now. Change the plot range to something smaller. With this blue graph going up and down, you can see the amplitude is getting smaller and smaller. So the blue graph is supposed to represent, say, the left-right position of the mass. Starts out at position 1. That position goes down because the mass is moving to the left, becomes negative as it passes through its equilibrium position and heads toward that wall, but it's not going to touch the wall. Reaches some negative minimum before it turns around again, coming back this way. And it's oscillating with a smaller and smaller amplitude because of friction. The red graph is the velocity. It starts out negative because, well, actually, I'm probably not letting the mass go from rest here. I've given it a little kick to begin with. The slope there looks like it's close to 0, but it's not exactly 0. It's a small negative number. Then the mass accelerates as it moves in the leftward negative direction. So the velocity becomes more and more negative. You're moving faster in the negative direction. Right here, the velocity is 0. That's when the mass is closest to the wall before it turns around and starts moving to the right. That's a positive velocity. If the position graph has an amplitude that gets smaller and smaller, so does the velocity graph as well. Do notice also where this red graph is positive, that's where the blue graph has a positive slope. Where the red graph is negative, that's where the blue graph has a negative slope. The red graph is the derivative of the blue graph. Not going to require you to do this on your assignment due Monday, but the last thing I want to show you is that you can use Mathematica to make animations. And, well, one quick animation I can do here, for example, is I could change how much of these plots get plotted. Let me do a little funny thing here. I'm going to change the right endpoint of the plotting window to be, instead of a 10, how about B? What's B? B is what I call my animation parameter. I'm going to put this plot inside another command called manipulate. Don't worry about the syntax. I'm going to start B at 0.1 and let it go up to 10. And the graphs get animated once I play this. That's like I'm watching the graphs happen over time as one example animation I can do. Now, you might say this is not a big deal. How is this different than my calculator? Okay. There's lots different about Mathematica than your calculator or Desmos for that matter. I am not lying when I say this. Any computation I personally can think of doing, or any visual I personally can think of imagining, I can make Mathematica do. It's super powerful. You're not going to have to do everything in this class. You're going to do basic things, okay? But if you get good enough at Mathematica, you can do anything in math that's computational or visual. Anything. I can't think of a single thing that I can't do computationally or visually. Now, it can't do proofs for me, although maybe it's got some artificial intelligence these days that can do proofs just like ChatGPT, but I haven't experimented with it.